So beyond these remedies, you cannot, even if you perfectly ensure that the temperature is minimal, the bandwidth is minimum, the resistance value is minimum, some amount of noise will always be there. So perfect solution for thermal noise is not at all possible. So definitely you will have some minimal amount of noise present in the circuit. You have to live with that. You cannot completely eliminate thermal noise. And we have been speaking about the noise bandwidth delta F throughout the thermal noise expression, right? So the noise bandwidth can be computed using this equation. So it is the bandwidth of the system. So if I am going to integrate from 0 to infinity, which means I'm going to cover all the frequencies, because thermal noise is applicable for all the frequencies, right? So I'm going to integrate from 0 to infinity h of f with the transfer function of your receiver. And whatever peak value I have, I'm dividing it, because I'm taking the RMS value. Here I am not taking square root. Integration is going to be mean, right? So I am integrating over the entire receiver transfer function from the frequency 0 to infinity, and I am dividing the peak value of the transfer function. So by this method, if I find what delta F I get, I am going to call that as a noise bandwidth. So you have one more bandwidth called 3 dB bandwidth in your amplifiers, and don't confuse the 3 dB bandwidth and noise bandwidth are not at all related. They are completely different in concept. So 3 dB bandwidth will ensure that between those two frequencies you will have maximum power gain, but this noise bandwidth will say that it will fix the power which is generated by thermal noise in a resistance. So this delta F will dictate what is the noise coming out of your resistance. But this 3 dB bandwidth of an amplifier will say the two frequencies within which if you operate, you can have maximum power coming out of your circuit. So the term says both are bandwidth, but logically if you see, the noise bandwidth and 3 dB bandwidth are not perfectly the same. So that is why in the book also they have given clearly that they are not logically the same. And HPK is the peak value of the receiver, and transfer function is going to be output by input. So for different various frequencies, you find the value, you divide the output by input. What function you call it as? You're going to call that function as h of f. H of f is called as the transfer function. So by uh, by logic, we say that the thermal noise is constant, but actually thermal noise is not constant. It's going to increase with frequency. So if you increase delta F in the equation for thermal noise, my power available at the receiver is also going to be, noise power is also going to be larger, right? So ideally, we can say thermal noise is constant, but practically what happens, it is going to increase with the frequency, which is practically observed in wireless communication circuits. And when you operate at a very high frequency, say 80 terahertz, they don't find any variation of the thermal noise when it is found at low frequency. Okay, so when you operate at a very high frequency, when you operate at 80 terahertz, you measure thermal noise, you get some value. When you do the same thing at 81 terahertz, you get a different value, but but those two values are not so much far away. So there is hardly any difference between the spectral densities. About up to 80 terahertz, they say there is no variation in spectral density. So it starts varying only after 80 terahertz. See, giga is 10 power 9, tera is 10 power 12. So we go into optical frequencies. So we slowly move into optical frequencies. Only in that frequency, they say till optical frequency, there is no difference between the spectral density of thermal noise. Only when the frequency enters the optical domain, they say that it starts showing a small variation in the noise power available in the system. And this thermal noise is a very, very dominating noise, and it is one of the most uh, powerful noise which can disrupt the complete wireless communication system. So the antennas can pick up these thermal noise very, very easily. So this thermal noise has a very strong connection in wireless communication system.